Thank you, sir, for accepting our invitation in the talk.
Thank you.
Thank you, sir. So, with your permission, then I'll start the session.
Yes, please.
Yeah. So, dear participants, so we have come for the session 12. So, one of the sessions we know that you are looking forward to, Hemant's session, and said topic would be the Indian seismicity and performance of ERM structures in past earthquake. So, we are glad to welcome him. Sir is BIS chair professor in the Department of Civil Engineering, IIT Guwahati. He is also Dean Online Education and Skilling since January 2025. Sir has earned PhD in Civil Engineering from IIT Kanpur, MTech in Structural Engineering, and BE in Civil Engineering from BNIT Nagpur. Sir held a progressive roles at IIT Guwahati and led a very good team. Assistant professor, he was joined 2007 to 14, and then associate professor from 14 to 18, and professor since January 2019. So prior to joining to IIT Guwahati, Sir served as a project engineer at Hindustan Builders Nagpur. He was also senior project associate and senior project scientist at the Department of Civil Engineering, IIT Kanpur. Sir research expertise lies in earthquake resistant design of structures, nonlinear behavior of structures, retrofitting of structures, seismic vulnerability assessment, vernacular houses, earthquake damage surveys, disaster risk management, and many more. So Sir is an eminent researcher with over 105 publications in all top tier journals and achieved more than 3,300 citations. Sir has numerous high impact publications in journals like Journal of Materials in Civil Engineering, Engineering Structures, and many more, and contributed to seismic course and guidelines. So Sir has recognized for his work on infill frames, unreinforced masonry, sustainable seismic resistance construction. Sarah's contribution significantly advanced earthquake engineering practices in India, particularly for vulnerable masonry RC structures in seismic zones. Sir, we are truly honored to welcome you, sir, and would like to express our sincere gratitude, sir, for your precious time.
Thank you, Susanta.
And one more thing, sir, I get this platform to express my views. Like when I did my PhD, and that is related to seismic behavior of masonry structures. And when I started doing the literatures and all those, we used to read all of your papers, and we learn from you. And every papers we read and we study about this. And we should say, like, I can still remember, sir, one of the paper I saw first time, that is the stress strain characteristics of masonry, brick masonry under uniaxial compression, which was published in Journal of Materials in Civil Engineering. There, sir, has given in 2007, and there the modulus of elasticity of masonry expressions, compressive strength of masonry expressions were given. Later on, it was included in IS 1893 2016, but Sir has in Sir's papers that already has given in 2007, and that time we used to calculate using your expressions and all those, sir.
Thank you, Susanta.
Thank you,
And
sir.
thank you very much for inviting me to interact with these participants here. So let me share my screen. Is it visible?
It is loading, sir. 1 minute. Yes, sir. It is visible.
All right. So today I'm going to speak about um, how the unreinforced masonry buildings have performed during last several earthquakes, not only in India, but also in other countries, and also some very simple and cost-effective strengthening techniques that we can use. In fact, anybody can use for these vulnerable structures. The figure that you see here is very interesting. You can see, I don't know the location of this, but it shows that how vulnerable these structures are and how innovative some people are. So somehow they found some technique to uh, keep this wall in its own place. Otherwise, you can see that this is at least 7-8 meter high wall. What would happen if it would fail? Now, although it is innovative, it is not engineered. Right? Somebody thought something at the last moment and they did something just to prevent the catastrophe. Now, such situations, you can see that they are throughout India. You can find such things throughout India, throughout the world. So let me first start with the Indian problem. This seismic zonation map that you are seeing is the older seismic zonation map, where you have zone 2 to zone 5. I did not get time to change this figure, but anyway, the uh, intent, what I'm going to say will remain same. Here you can see some circles or some ellipses on different colors and different sizes. So basically what I'm going to show here is the population density versus the density of unreinforced masonry buildings superimposed on the seismic zonation map. Now these circles, the color of these circles, they indicate the population, and the size of the circle, it indicates the density of the unreinforced masonry building. So basically you can see that red color means they are highly populated. And also when the circle is bigger, that means that the density of URM buildings in these areas is also high. You can see wherever there are bigger red circles, these are the areas of very high vulnerable URM buildings. Then comes the blue circles. Then comes the yellow circles. So all these combinations, you see, we have almost 80% buildings in India that are constructed in unreinforced masonry. And that's how you see these circles everywhere. Some places you have bigger circles indicating large number of these buildings. We also know which are the populated areas from these colored circles, and also which are highly seismically prone areas from the seismic zonation. So this figure actually shows the very high seismic risk that we are seeing here. Now, huge stock of unreinforced masonry buildings in populous areas with high seismic intensity. That is the problem. Now, the question is, how do we deal with these problems? So we'll try to answer that toward the end of this presentation. But let me first take you through how these buildings have performed in the past. So, I mean, I can go back, 50 years, 100 years, but let me start with the start of this century. So 2001 Bhuj, Gujarat earthquake has seen numerous such failures. In fact, villages where all the unreinforced masonry buildings collapse. So one figure, one photograph you can see here. Most of these buildings, which were unreinforced masonry buildings without use of any steel, they collapsed. So there you have the simple residential houses of people. Then you have some palaces. You also have some temples and so on and so forth. Some minars and some brick kilns. Huge number of such structures collapsed in Bhuj. Now the question is, why did they collapse? Didn't we have the seismic codes or even non-seismic codes for design of these buildings? Don't we know the design of masonry structures? Don't we have the good material? So all these things that come to our mind when we see such failure. Now, it is not only the problem of India. So you can see here in Iran, huge number of such buildings collapsed during the Bam earthquake. Now, this left figure is not exactly unreinforced masonry building, but barring some reinforcement in the form of steel beams, every other thing is here. All these walls, they're not really confined using these elements. So therefore, you can see the failure of these elements. In fact, the complete story, 2 stories, they collapsed here. And you cannot see anything, any house here is completely collapsed. Kashmir, in 2005, we have seen how unreinforced masonry buildings have behaved. And here we found that there are large number of buildings were uncourse rubble masonry, which is even more dangerous because of the nature of the masonry, the units. These are not uniform, and it's difficult to place the mortar in the joints. Now, how will you characterize this damage? Which type of damage is this? In China, 2010, see, these are mud masonry buildings, mud mortar masonry buildings. And again, different types of masonry used. Here there are stones, here there are slates. And you see the thickness of the walls, the thickness of the slab, huge. So the mass of the building, it's really large. And of course, the stiffness of these buildings is also large, attracting more forces, but the strength is very less. The tensile strength in particular is very less. Shear strength is very less, so these buildings suffer these damages. So this is completely out of plane collapse of these walls. In Haiti, Haiti is a country in uh, Latin America, between the North America and the South America, and you can see huge palaces constructed of these unreinforced masonry collapsing in 2010. Large number of people died during this earthquake. New Zealand, so the developed country, and what happened during the twin earthquakes of 2011 was really astonishing to many people. But then they have some very old structures. This was a church which collapsed during this earthquake. They were completely unreinforced masonry. And after the collapse, they had series of discussions for several years, like how are they going to retrofit it, or how are they going to actually reconstruct it. Nepal in 2015. So we have seen what has happened during that. So many darbars in Nepal. So they have primarily 3 darbars where there are several temples, several palaces, these buildings, which are constructed using only unreinforced masonry. Look at the thickness of these walls, again, very thick, and the thickness of the slabs. So, like I said, most of these buildings collapsed during that earthquake in 2015. Now, these are some of the common observations, which you already have seen that, I mean, not necessarily here, but we already know that which are the most vulnerable areas in any structure. So these are the areas of the walls near openings, because these are the areas, these are the corners where there are huge stress concentrations, and the damage starts from there. And if we can somehow restrain the damage at that location, we can improve the performance of these buildings. And that is what we will try to do. And I'll show you some results, how we have done this. Then, of course, the out-of-plane collapse of the walls we have seen in almost all these buildings. Why does this happen? It happens primarily because there is a limited connection between the perpendicular walls, between the wall and the slab, and between the other elements of the buildings. So when you don't have proper connection between the wall, the perpendicular wall, the connection of the wall with the perpendicular wall and the slab, this wall is going to fail during the earthquake in the out of plane direction. What we have seen during most of these earthquakes, that the traditionally constructed masonry buildings, which are reinforced or laced with some kind of wooden material like timber logs or bamboo, they survived. There were, of course, some damages, but they survived. So we conducted a significant amount of research on some buildings here, but today I'm not going to show you those results. But these are really interesting buildings where people did not have any design codes or calculations or guidelines, but through their own experiences, they have come up with some building typologies. Then we also observed shear failures in these walls. Of course, where we have larger openings and where we have more number of openings. Obviously, there will be openings in the walls. So we have certain codes I'll discuss later. They have some criteria on openings. Then when we provide certain bands in the form of lintel bands or the sill bands and the bands at the slab level, the plinth level, then we have seen that these buildings have performed slightly better. But if we connect these walls together with these bands, then the performance improves drastically. Now, we have seen some retrofitting done in these buildings, but then It is not common because we have limited design and construction guidelines. In fact, there is no detailed guideline or codal provisions which are available to common people. So one such technique which people have used is strengthening of the building using some steel elements. Steel elements can be used in different forms. So this building, this is a mosque in Port Blair during the 2005 Sumatra earthquake. Many buildings in Port Blair collapsed, but this building, though it was unreinforced masonry, did not collapse. You can see here, these are the steel bands that were applied on all these walls in different ways. So what is the reason they applied here? Because there was an arch here. So there was an arch roof. So just to provide support to that arch roof, they provided these bars which were continuous along the length of the building. And on the outside, they connected the bars on both the faces using these steel channels. Similarly, diagonal bracings were used in some places. This is the building from New Zealand. The steel flats were used on the faces of the building. This is a building from Sikkim. And this building survived 2006 and 2009 earthquake without much damage, though there were some damages. Again, bracings. So people have used these steel elements in different ways without worrying about whether some codes are available or not. So there are no codes available who can give you some design criteria or calculations for calculation of these amount of parts. But people have used that. And when people use some simple strengthening schemes, these buildings have survived. So that means even minor retrofitting or interventions at correct time, can influence the performance of these buildings and save these buildings. Let us look at what are the provisions given in some of our codes. So we have a very old 4326 code which will be replaced now, but there are some interesting provisions here. It has given some recommendations for the dimensions of openings. If you look here, any unreinforced masonry wall may have a door opening and multiple window openings. So they have given some recommendations for the mortar mixes, what kind of mortar can be used, and they've also given recommendations for these dimensions. So you have the door this much away from the cross wall, you have the door this much away from this wall. What should be the height? What should be the width? All these dimensions are given. But these are only guidelines. So these are some of these dimensions for the size and position of openings in the bearing walls. They've given that, but other than that, there are no provisions for the strengthening. They've also given some provisions where lintel bands, roof and floor bands, and vertical bars can be provided at specific locations. So this is the lintel band, this is the slab or the roof band, and you can see here that how much reinforcement can be provided in these bands of different sizes, right? So these details are given there to improve the performance of these buildings. They also say that you can provide some vertical bars in the walls. So these dotted lines here, these are the vertical bars. Here's another code 13828, again very old code. It will again be replaced, but it also has some provisions on how to improve the performance. So they say that you provide alternating tooth joints in walls at the corners and the T-junctions. So which is generally used by the masons. It also says how to strengthen the masonry around the opening. So basically they say that you provide some reinforcement bar around the opening to improve the performance, because of the known issue that these are the places where we have huge stress concentrations. So these issues are known to us, known to everybody, that we need to strengthen them. But then you can see yourself how many buildings have these steel bars or these bands at different locations. Another retrofitting scheme, or here this is not retrofitting, but the repair scheme proposed by the code is grouting or epoxy injection. So whenever we have weak walls, we can inject this grout or epoxy. One interesting scheme proposed in the code is using the pre-stressing bars, strengthening of the walls by pre-stressing. This is extremely difficult because it depends on how is the quality of the wall here, what is the strength of the wall. But anyway, the method is given, and I've seen some buildings strengthened using this scheme. This code 13935 has another interesting strengthening scheme. It says use splint and bandage technique for the strengthening. Now, splint and bandage are these members, horizontal members and the vertical members. So this is the bandage that we provide around the building to keep it to keep these walls together. So this splint and bandage technique can be used in a variety of ways. So they have also given some guidelines on what kind of wire mesh can be used here. Now, though these informations are there in some of these IS codes, but then the most important detail about the tensile strength of masonry, about the strength of these steel elements or any similar strengthening elements, the elements which are used to strengthen are missing here. There's no information or a particular type of strengthening scheme or a particular requirement. So we cannot use every scheme for every purpose. Right? So we have to first find out where is the vulnerability, what kind of strengthening is required. Then only we can think of developing a scheme. We require special material and skilled labors for some of these techniques. For example, the pre-stressing, right? It's not easy to do. The diagonals, not easy. So these are, of course, we need the materials which are not available locally, as well as the labor which is not available locally. So it becomes very expensive. And when it becomes expensive, people do not tend to use these strengthening schemes. There are a few methods which are very simple and which are inexpensive, but there are no design guidelines. For example, the splint and bandage technique, the steel flats, all these are really simple. They are inexpensive. Material will be available, but there are no guidelines. Like what is the size? How much is the thickness? What is the strength? That is not given. Only the broad guidelines are given without any reference to the capacity or demand. So then we thought that let us try to see what is the effectiveness of some of these very simple techniques in strengthening these walls. So what we did, we considered a full scale wall. This is 3 meter height by 3 meter length. And we considered 3 types. So one wall with door, one wall with window, and one solid wall without any opening. We tested these walls under the quasi-static loading that is applied at the top of the slab, the top of the wall. This is a RC slab. It's a simple quasi-static test with very low frequency, without worrying about the inertial or the damping effect. And just to compare how these buildings or these walls behave in comparison to each other. These are some of the properties of the bricks, the mortar, prism, all that. And this is how these 3 walls perform. So as we expected, a single story wall will obviously have failure at the base. And also there are some cracks formation at the top. When we have these door opening, we have the crack started forming from the corner and at the base as well here. In case of window opening, and you can see here in case of door opening, though we have this lintel band here, it was not a band, but just a lintel, the crack formed here, but it started moving horizontally instead of moving diagonally. And after the lintel band was terminated, it then started moving diagonally. In case of window opening, again, we saw the horizontal crack at the base because it was a single story. Axial load was very less here. And why the cracks did not form here? Because there was a lintel and less vertical load. Let me show you one video here that will give you some idea on how brittle these walls are. I'm sure you must have seen some videos or some failure mechanisms in case of reinforced concrete frames, how ductile they are. But in this case, you will find how brittle they are and how quickly they fail. You can see here that we have started applying the load here at the top. I'm showing you this video in a fast forward manner, but the actual test was conducted very slowly. You can see here the displacement, which is applied at the top using this servo controlled hydraulic actuator. And you cannot see any damage so far in the wall, though you can see the people movement there. But then suddenly we found that instant this type of failure. And we had to stop this test in an emergency because immediately it failed. And because it was just a single wall, there was nothing that was stopping this wall from falling in the out of plane. So this is a very sudden failure. And you can see here, I'm comparing the hysteresis loops for the three frames, for the three walls. The first wall is this red, second one is the wall with door opening, and the third one is the wall with window opening. And these are the peak points. These are the same figure, but without hysteresis. I'm just showing the envelope of these curves. So you can see the presence of door here reduced the strength as well as deformability of these buildings. And obviously we have seen that the crack started forming right at the door opening. So it failed immediately. Now, how much is the displacement that it went up to? It is about 7 mm. And that is how you did not even feel that, you did not even see that on the computer screen. So 7 mm displacement, it failed, which is very, very low from any standards. Then we thought that it's not fruitful to just test one wall. So we tested the entire building. So this is a full scale 3 meter by 3 meter by 3 meter building, which was tested in our laboratory at IIT Guwahati under quasi-static loading using the servo controlled hydraulic actuator. And then we strengthened this building using this steel flats. So one scheme was there in which we used one steel flat throughout the building at the lintel level. Then we used another scheme where we used the steel flats at the lintel level as well as at the sill level. Also, around the openings, all around the openings, we use these steel flats. And these steel flats were also provided on the inner face, you can see here. So wherever you see steel flat here, same steel flat was there on the opposite face also. And then we connected these steel flats using a bolt. So at regular intervals, we connected them. So this is a very simple technique. We don't need to damage this building. There are no chemicals used on these buildings. Very simple, very quickly done, and it's very inexpensive. Local material, local labor. This is how different walls were. So this is wall 1, the solid wall. Wall 2 is with the door opening. Wall 3 is with the window opening. And this is again 3-star, the wall with the window opening, but in the out of plane direction of this loading. So if you remember the previous figure, we have already tested wall 1-star, wall 2, this is door, and wall 3. So these 3 walls we have already tested in the in-plane direction. So we know individually what is the strength or what is the capacity of these 3 walls, but that is individual. So here we will see what is the capacity of the entire building when we join these 4 walls. Simple. without using any steel flats or bands, and then with the use of the steel flats. So this is how the steel flats were provided. This gray members here, these are the steel flats, and they were connected using this nut and bolt arrangement at every 0.5 to 0.7 meter. So this is clearly given here. So let me first show you the test that we conducted for the unreinforced, unstrengthened building. And then we will strengthen this using steel flats. So here I'll show you the instant where the cracks start here. So this happened at a lateral displacement here at about 17 mm, 17 to 18 mm. Now, when that happened, you can see that though the failure has taken place, but because it is a three-dimensional building, the building starts rocking. This is called a rocking type of behavior. So you can see here that we are applying the load in a cyclic manner, positive and negative. But though it has failed because of four walls connected together, the building stood there. And you can see the crack formation at different places. So these are the four walls that I just discussed with you. And you can find this is a wall 1, solid wall. So this is how the crack started in wall 4 at the window opening, and it continued into wall 1. Here also at the base of this opening, the crack started, and then at the junction of the wall, so it separated the two walls at that location. This wall 3 from outside, you can see cracks emanating from these openings and then spreading towards different region. And this is wall 4, wall 2 from outside. Again, I mean, the thing that we discussed, that these are the areas which are more vulnerable. So you can see that these crack formation throughout the length. So this wall 2 and wall 3 are the adjacent walls. And then this side is the wall 4. So this crack continued throughout the length of the building. And therefore, this top portion of the wall, it started rocking. Then we strengthened it using very simple, just one band here. Now this is applied externally. There is nothing, nothing that was no cement, no mortar, nothing. Simply we drilled the hole, and with the help of the nut and bolt, we connected this steel flat to the wall on both the faces. Let us see how the building performed when we have this. So now we reached 22 mm, at which these cracks were such large. Now you can see the rocking has reduced because of presence of these steel bands. This band is actually resisting the crack, because you can see the crack flowing through the steel flat, right? And that is what we want, that the crack should pass through the steel flat so that the strength is the strength of the steel flat comes into picture. So you can see here the cracks were still forming through the openings on all sides, all the walls. But then interestingly, what we observed, that even this steel flat, it broke at one location. So this is a very good thing for to see. Why? Because then we could demonstrate that the strain and the stresses in the walls are transferred to the steel flat. Now, when that happens, that shows that the strengthening scheme is working. Because you can imagine when the steel flat was not there, would not be there, then this would be an immediate failure. But when the steel flats broke or it failed, it must have failed with some ductility. So that is the beauty of this very simple strengthening scheme. There's nothing very complicated here. Then we added some additional members, the steel flat at the sill level, the steel flat around the openings, all around the building. And let us see how the building has performed. So at about 30 mm now, we see that this the cracks started appearing along the whole length of the building. But you can very easily see how the entire building is now moving instead of just movement of the top part of the building, right? And then it is holding these bottom part of the building, the steel flats, they are holding very nicely. Let us see the cracks. So now you can see cracks, of course, forming everywhere, because that is how the brittleness of the building plays a role, the low tensile strength of the masonry plays a role. There will be cracks, of course, but the steel flats, when they are there, which are restraining these cracks and they are resisting the load, that is what we want. Now, what we did in all these steel flats, we used large number of strain gauges. So you can see here in all these walls, external as well as internal, all these numbers, they indicate the strain gauges. And wherever you have this red strain gauge, we found some significant amount of strain development. And this is the strain that was recorded in these strain gauges. So I'm showing you the result for the scheme 2 or the model 2 at 30 mm displacement. Now at that displacement level, which was applied at the top of the building, there are the strain gauges which has crossed this yield strength of the steel, which is about 2 into 10 to the power 5 MPa. So, see, they have reached the yield strength, several strain gauges. That means the steel flat was actually deforming, was actually taking the load, sharing the load from the building, and therefore the performance improved. And these are the comparison of the hysteresis slopes. So this is the hysteresis curve of the unreinforced masonry building. This is for the scheme 1 and this is for the scheme 2. You can see how drastically the performance was different. And we'll compare the envelope curves. So this is unreinforced masonry, the scheme 1, marginal increase in the strength, but significant increase in the deformability that we have seen. But when we use the scheme 2, you can see there's a significant increase, about 30% increase in the strength and about, I think, 50% increase in the deformability. So that shows how effective these very simple strengthening schemes can be in case of the unreinforced masonry building. Now, why is it has become effective? That is because the original tensile strength of these URM buildings is very, very low. So even when you have very simple member that is trying to resist that tensile load, the performance of the building improves drastically. These are some of the major observations which I have already discussed, that the load carrying capacity of the strengthened building increased by about 38%, which is good. 38% increase in strength is good, but more importantly, the lateral deformability of the strengthened building, it improved significantly by about almost 50%. That is what we were looking for. How do we delay the failure? How do we delay the brittle failure in these buildings? Of course, the final failure will be brittle, but then the delay is very important for such brittle structures. Then the hysteretic response was more stable and it was better for the strengthened building that we have already seen. And from the strain gauge readings, we found that the corners of the openings, these are the most critical areas needing special attention because there were more strain at that location. We can significantly improve the lateral load behavior with the help of these steel flats, and we can reduce the vulnerability. The advantage of this is we can very easily replace these steel bands. Even when they fail, we can simply remove them and provide additional steel band. And that is what was done in the Sikkim building, if you remember that figure. I showed you one photograph where the steel bands were used in Sikkim one building. That was an archive building in Gangtok. So the motivation of this study came from that earthquake visit. So they used to replace these steel flats once they corroded, once they were found to damaged, whatever is the reason for that damage, earthquake, non-earthquake, they used to replace them very easily. And that is one of the major advantages here. Now, once we had all this, then the next stage is to find out some design equation or some method to know how much steel flats are required for a particular wall or for a particular building. So then what we did, we simulated these walls and the buildings in some software. So we use two software. One is Strand 7, which is specifically developed for the unreinforced masonry buildings in Europe, and Abacus, of course. We use both these software just to check our results, and we were quite happy with the way both these softwares were modeling the failure. So you can see the crack formation in both these models, in Abacus as well as Strand, and in the same location. Wherever we found experimentally, we could simulate the similar behavior in the numerical models. So the next stage, once we have the numerical model ready, which is validated with the experimental study. So this figure shows the validation. The next stage is to do some parametric study, basically to develop some understanding on how different parameters uh, uh, affect the strength and the deformability of these buildings. So this is one validation figure that is shown here, numerical versus experimental. So Strand 7 couldn't do nonlinear after a level, but then Abacus, we could do a nonlinear. This is the numerical analysis in which we use different sizes of the steel flats. You can see here 1 mm thick by 5 centimeter wide, 1 mm thick by 10 centimeter, 1 mm thick by 15 centimeter, 1 mm by 20 centimeters. 4 different types of steel flats were used. Here we used same width of the flat, but we changed the thickness of the flat. Right? So 1 mm, 2 mm, 3 mm, 4 mm, keeping 5 centimeter as the width of the flat. And this is for the scheme 1, and these results are for the scheme 2. So you can see here, very interesting thing that we observed, that it really did not matter what is the size of the steel flat. Even for the very low 1 mm by 5 mm, 50 mm steel flat, the performance was really nice. And we go on increasing this width of the steel flat, it did not matter. The strength was more or less same because the failure was occurring in the masonry. So masonry is weak. It does not matter how strong or how thick or wide this is. There was a minor difference when we used thicker steel flats, but then you can see here most of these results are lying in the same along the same region. In the second method also, the type in the scheme 2 also, whether we increase the width of the band or we increase the thickness of the band, it really did not matter. But if we increase the tensile strength of the masonry, then we have significant variation in the performance. Right? So the conclusion from here is, though we provide very small band, the performance increases drastically. And that is very interesting. Then based on all these results, I'm not showing you, by the way, all the results. We used several other things. For example, the um, aspect ratio, the thickness of the wall, the area of cross section, of course, we have discussed, and then the tensile strength of masonry. We used different tensile strength, different aspect ratio, and different thickness of the walls. So some of these, I'm just showing you some results, but not all here. Finally, we carried out the nonlinear regression analysis for all this data that we developed. And this is a very simple equation using which you can get the strength of the strengthened building, the lateral strength of the strengthened building, right? So just you need what is the tensile strength, what is the aspect ratio, thickness of the wall, and cross-sectional area of the steel flat. So alpha L is basically the ratio of the strength to the self weight of the building. So it is basically you can directly compare it with the seismic coefficient that is given in IS 1893. So they are directly comparable. And when we compared it with the experimental results, the error was about 18-19%, which seems to be high, but then in those who work on masonry, they will appreciate that this 20% error in masonry is very, very low. Because masonry is a very uncertain material. Now, there are numerous other methods which people have used, even in IIT Guwahati. There are students who are working on other methods of strengthening of URM, because this is what we are going to what we will need in next 10, 20, 30, 40 years, because so many unreinforced masonry buildings are there, and we have to reduce the seismic vulnerability. So we need these simple strengthening schemes. So people are using ferrocement bands. This is one such study that we are conducting, where we used similar full-scale building with ferrocement bands in different ways, different manners. Then people are using FRP wraps, steel diagonals in the walls, and also at the slab level, horizontally. So they provide steel diagonal bands there. Then shotcreting, so basically put micro concrete on the surface of the wall. Post-tensioning, I've shown you some figures, which one of our IS codes they say. Then the mesh wrapping the entire walls, and so on and so forth. There are so many methods, so many techniques available in the literature, some without any guidelines, just something people have suggested without testing. Some methods are given in the codes, like in our codes, and for some method, there are some detailed guidelines are given in international codes. For example, the ferrocement bands, there are some very detailed international guidelines available because people have used them previously. For FRP wraps, not much guidelines for the masonry, but for concrete, you have very detailed guidelines, and so on and so forth. So this is what I have. Let me thank Hemant, who was my PhD student, who carried out all these studies that today I have discussed with you. The strengthening of the unreinforced masonry buildings using steel flats, surface-mounted steel flats. The study was supported by the Department of Science and Technology, so I thank them for the funding. And thank you everybody for listening to my talk patiently. If you have any questions, we can discuss.
Thank you, sir, for the. Thank you, sir. Am I audible?
Thank you. Yes, you're audible.
If you question, the question I received, like whenever we can see the earthquake vulnerability and the seismic vulnerability, that time we may notice in the tall structures. Though being the masonry structures which you have shown, these are the low-rise structures. So what is the major causes behind of it? So it witnessed the catastrophic failure.
It's basically, this is a very brittle material with very low tensile strength. That is the basic problem. And people use different types of masonry without worrying about joints at a particular location, like between two walls, between the wall and the roof. All these locations, people don't provide proper joints. But inherently, the material is brittle and very weak. That is the basic reason. So we need to provide some steel, or our construction should be such that the connection is proper, the walls are thicker. For example, if you look at some of very old structures, they are still standing, right? Because we have taken care of them, we have maintained them properly, and they were designed like that.
Yes, sir. Very true. Sir, one of the experiment you I noticed, like you have added some artificial mass on the top
Uh,
of the building.
no, that was basically the dead load and the live load on that building. So 3D building, it had on the slab top, the mass that is coming from the top that was placed.
Yeah. So is it a cement bag kind of thing you placed or something else or plate?
We placed the plates, the steel plates.
Okay, steel plates. And sir, though we know like the direction of earthquake is random, so you have showed one direction of the loading. So how much results we can expect to differ, like the one directional, or if it is a real time, earthquake testing, if it's there in the building, then is there any noticeable change we can find in the failure pattern?
There will be. So if you remember the figure, the direction we tested for this building was the weaker direction. So there was a door in the in-plane direction, and there was a window opening in the in-plane direction. So this was a weaker direction of the building, which we tested under the quasi-static loading. If you apply the loading in the perpendicular direction, the strength will be more than this. And that is the precise reason we tested in this direction.
Okay, sir. Participants, if you have question, you may drop me the message. Maybe later I will send it to sir and compile it and give you back. Sir, thank you, sir, for very informative sessions. Again, for accepting our invitation. So always we look forward to your talks, and probably I have attended many of your sessions, online sessions, though we are interacting first time.
Thank you.
Yes, join.
Yeah, Dr. Sushanta, I think it is breaking.
Is it fine, Robin sir?
Yes, yes.
Yeah. Okay. Thank you, sir, for the wonderful session. Actually, I've followed many of your sessions, online session, and it was always new things to learn from you, sir. And though
Thank you,
we are
Susanta.
interacting first time, yeah.
Thank you. Thank you,
Robin sir,
Robin. Thank you, Susanta.
thank you, sir. Robin sir,
Yeah, thank you, Professor.
yeah, sir.
Yes.
If you give me one moment, sir.
Yeah.
One moment, sir. Ajay. Ajay. Sir, thank you again for sparing your time, sir. Would like to present a small token of thanks from our side. Please accept it.
Okay, I accept it. Thank
Thank
you.
you. Thank you, sir.
Yeah,
We'll
thank
be,
you, Professor Hemant. Yeah.
Thanks.
and sir,
Bye-bye.
we'll be looking forward more of your session in future.
Sure, sure,
We'll be in touch.
sure.
Thank
Yeah,
you, sir.
thank
Bye.
you, Hemant. Yeah.